Okay, thanks Joe, thanks everyone. So I'm Cyrus, I'm from Livermore, I'm a computer scientist, and there I work on Visit. I've worked on Visit for about 10 years now. And I will say, coming to something like AppTesc, it's pretty awesome to, in the lobby here, you have all of your pictures and your one-pagers, I guess, about your research that you're doing, and I like to see nice pictures of Visit and a pair of you already on those things. So it's pretty rewarding for us as visualization people to see that you're using our tools and doing great things with our tools, and that helps, I guess, helps us blunt some of the bug requests and some of the pickier things that we have to deal with as developers of these tools. As Joe said, I'm going to spend the first 30 minutes here on slides. These 30 minutes of slides are in between you and your calories for lunch, so we might get done a little bit early. That's fine. I'll probably have some time for questions. And then after that, we'll have about an hour and a half where I'll give you a guided tour of Visit. So we're going to do this in 3 stages. So the first will be showing you how the tool works on basically some toy data sets. And then the second 2 stages will be more of a narrative-based thing where we'll walk through kind of asking and answering questions on some more complicated data sets. I'm going to do what any presenter would tell you not to do, or anyone who teaches you how to give a presentation would tell you not to do at the beginning of a talk. I'm going to tell you to go here and download Visit and get distracted. But so all of our exercises here are on our Visit Users Wiki, visitusers.org. If you search for tutorial, you will land there. There's a page for tutorial preparation. If you get here, it will tell you basically how to download Visit, how to install it, and how to get up to the point where you get your first picture. So here's the page, the tutorial preparation page. And again, if you go to visitusers.org and if you search for tutorial, you'll land there. And we're going to be using Visit 2.12.3. Visit 2.12.3 is actually installed on Cooley as well, so we'll show you how to connect to Cooley. But download on your local machine Visit 2.12.3, and then that will allow us to do most of the exercises. We'll actually do all on your laptop. There's example data sets there as well. If the data sets are downloading slowly, I would recommend downloading the tutorial data first. It's just generically called the tutorial data, then the water flow, and then the aneurysm, because that's the order that we're going to look at them in our exercises. I wanted to acknowledge this aneurysm simulation data set that we've been using for tutorials for a few years. That's courtesy of some folks from Swiss Supercomputing Center. A few years ago, there was a sort of a HPC computing challenge program in Europe where a lot of these aneurysm solvers were producing data and doing cool things, and we were able to get our hands on some of this data and kind of compact it down into a form where we could use it for tutorials, so we're very grateful that we were able to do that. All right, so on to the slides. I'm going to talk to you about the Visit project, what it's about, basically where it came from and some of its roots. I will say, so I usually start off with a joke about how Visit's a bad name, and it's hard to Google because if you Google Visit, you'll get Visit Hawaii or something like that. But over the years, Google's got smarter, right? So Google knows you've been sitting here for the last 2 weeks in the Q Center, so it probably thinks you're either an accountant, a consultant, or an HPC specialist. So you might be able to Google Visit. You might be able to actually find the web page. If you can't do that, then you can type LLNL Visit, because Visit came from LLNL, and that will help you get to our pages. And again, the visitusers.org is our wiki where we have a lot of content. So what is Visit? Like ParaView, it's an open source tool. It's a tool that allows you to do visualization analysis of mesh-based data, so scientific meshes. At Livermore, we do a lot of hydrodynamic simulations. That's what I'm very familiar with. It's a production end user tool, so scientists and engineers use this tool, not just visualization experts. It works on your laptop and it works on the world's biggest supercomputers. And the goal is to make those things look the same. Now the reality is some things are slower on the biggest supercomputer. Depends on how big your data is, right? It's open source. It has a BSD style license. It's been open source for quite a while. This particular picture I show here at one point so over 10 years ago now, was a very heroic simulation and a very heroic thing to visualize. So it's a Raleigh-Taylor mixing simulation run on BGQ at Lawrence Livermore. It's a regular grid simulation. I believe it was at that point run on about 3,000 processors, and it has 27 billion elements. So this thing was 10 to 12, 10 to 15 years ago, this thing was very hard to visualize. These things are kind of getting more common now. That just gives you an example of some of the stuff that we use Visit to look at. So Visit, of course, is good for pictures, as visualization tools need to be, and good for making movies, but that's not all it's good for. Actually, most of the poor simulations out there aren't destined to be, visualization showcase material or things like that. Most of them are at the whim of the people who ran the simulations, and they're getting chopped up and sliced and diced day to day. So one of the most important things that a visualization tool can do for you is help you with data exploration. So we have things in there to get into your data, ask questions, slice and dice, et cetera. You also want to put numbers to your pictures to help you back up things. So there's quantitative analysis features available. Joe has that great example about visual debugging where the blade disappears in the middle of the simulation. Visit and tools like Visit and ParaView are used to debug these things that just, some horrific things that happen in simulations. And there's features in there that are really meant for the developers of simulation tools, being able to click on things and get information in, basically in the index sets that you care about from your code and things like that, so expose that. Another important use case is comparative analysis. So this can be, what's referred to as the view graph norm, where you have two pictures and you'd like to see if they look the same. That's obviously something we can do because we can produce pictures and we can produce pictures next to each other. But we also have features that allow you to do more complicated things like map meshes from one mesh to another mesh and do subtractions and things like that. So that's helpful with comparative analysis. And then finally, I said, pictures are important, presentations are important. That's how we communicate with the public. That's how we communicate with our sponsors. So presentation graphics are a big point of what we do with Visit as well. Joe covered some of these primitives, so I'll go through them quickly. But just to let you know the types of things that Visit supports. So we have streamlines and pathlines. So again, streamlines give you an instantaneous view of a velocity field, basically by advecting little particles through your velocity field at a specific time. And pathlines extend that to integral over time, so it's actually like you advect things across your simulation. We support glyphing with vector and tensor glyphs. The bread and butter of all scientific visualization is pseudocolor rendering, so of course we support that. That's the thing that gets most clicks on all these tools is pseudocolor rendering. We support volume rendering. So again, this is the concept where you're casting rays through your data. So it's sort of like an X-ray with magical colors attached to how it interacts with it. We have some support for molecular visualization, although there's domain-specific tools that honestly do a very much better job of this, but we have some support for this. And we also have some interesting, kind of on the fringes of InfoVis stuff. We have parallel coordinates as a plot. Parallel coordinates in this context, we really use it to try to select other things in our other plots. That's the main thing. But we don't do too much information visualization stuff other than curves and things like that. So Visit uses MPI in order to get the job done on supercomputers. So that means we're using distributed memory parallelism. So your data set is chopped up into lots of smaller chunks. This is the data set that I showed you on the first page earlier. And again, the full data set is about 27 billion elements or billion little blocks. And in reality, it's partitioned, in this case, over about 3,000 smaller grids. And tools like Visit and ParaView have the magic in order to put those things back together in a way that gives you, the coherent picture. So, MPI has been dominant for a long time. Obviously, with exascale on the horizon, there's more of a focus on node-level parallelism. So in that case, you're going to have to be using threading or things like CUDA in order to get the job done and get the parallelism at a smaller fine-grained level. So Visit is working on that. Our team's working on that. We're working with the Kitware folks on a product called VTK-M, which you've heard about VTK. VTK-M is a recasting of that to run efficiently on multi-threaded or mini-core processors or GPUs. So we're getting some of that stuff integrated into Visit, and it's going to be important for the future. So history of Visit. So Visit started out at Lawrence Livermore. At the time, it started out around 2000, the year 2000. And at the time, it was internal, and it was a prototype, and it was built up over a few years. And then all of the simulation users at Livermore basically they needed a tool that could render their render data from their big simulations. Eventually, over time, we transitioned them from an older tool called Mesh TV to Visit. And from that, Visit grew over the years. We released it open source. We had engagements with other parts of the DOE, so not just NNSA, but also Office of Science. We have collaborators at universities. There's a lot of different people who use Visit, Department of Defense, et cetera. So we're currently under active development. We have I'd say it's about 20 people who work on the code, not full-time, obviously. At Livermore, we have a team of 5 people who mostly work on it. But it's a distributed development effort, multiple funding sources across DOE. The timeline stops in 2017, but the story doesn't stop in 2017. I just haven't updated it. So we have some ECP engagements related to in situ and some other Office of Science things we're doing. We're constantly moving forward. So our goal is to make a tool for people to use. So in support of that, we have regular releases. We have lots of different documentation. We've focused a lot on these tutorials because they're the quickest way for people to get up and running. So those are available online. We do have a manual. The manual is under update. The one you will get is horrendously old. I apologize for that, but we're moving to a new technology, Sphinx, in order to do our manuals, and that's kind of a work in progress to update all of our content. I think one of the reasons why we focus more on these tutorials is that oftentimes a 300-page manual isn't tractable for people to sit down and do these days because there's just too much competing for their time. So they will just, those who would do the 300-page manual will just email us on the users list instead, right, and ask us how to do things. So we do have, I'll talk about those lists, but we do have support lists that makes it easy to contact us. Joe talked about data representations earlier. Visit supports, all different types of meshes, primarily through VTK, although we also, again are going to be using VTK-M, and we have some high-order support outside of VTK through MFEM, which I think you were introduced to earlier in this program. So the basic things there, structured, unstructured. We have scalar vector tensor fields. We also have support for things that are really core to some hydrodynamics codes like multi-materials, so material volume fractions, and some more exotic things like species, so mass weightings. So we have kind of first-class support for this in our data models. The first question is, of course, how do I get my data into Visit? The answer is could be very simple or it could be very complicated depending on what your data looks like. I like Joe, I recommend using a well-defined file format like XDMF or VTK. Silo is also a tool that we use at Livermore. That's what we use for our production simulation codes. There's if you have plain text files, if you happen to have plain text files, you might be able to swizzle some knobs and get some pictures up easily. We provide something to help you write meshes. It's called a Visit Writer. There's some details there. And there is another 100x page manual that you can go and go and devour. And it has source code examples, which is very nice. So how does Visit do its work and work on these HPC systems? So we have a client-server architecture similar to Paraview. So in Visit, you run the viewer, which is called the viewer, which manages all the state on your local system. And then there's various clients for the viewer. The one that you'll see most today are the GUI, which we'll be clicking around in, and also there's a command line interface, which is Python-based. And then the data processing happens in Visit's engine, which is the MPI part of the beast. So that can be running on a parallel HPC cluster. It can also run on your local system. So effectively, you have the parts that are controlling what you want to do over here, and then the parts that are doing the heavy lifting can be elsewhere. And as you'll see, we can connect to Cooley and start up parallel engines there. So I alluded to this a little bit in our earlier pictures. When you have this distributed memory parallelism, your data set is broken up across all these processors, which means none of them see the whole picture. So you have to have a way of putting that back together, particularly when you're doing parallel rendering. So when you do parallel rendering, you render parts of the bit data all across the supercomputer, and then you use a parallel compositing technique in order to get the image put back together. So Visit will automatically switch to running parallel rendering if you have a parallel engine going and it thinks the data is big enough or it needs to be done. You can also force it to run in scalable rendering mode, what we call it. It works for surfaces, but we also have volume rendering. Volume rendering runs at scale, so that's important. So we talk about Visit as an application, but it's also kind of an infrastructure for people to build on. So the mechanisms for getting your data into Visit, there's a plugin infrastructure there, and there's a well-documented process. If you had to write a custom plugin for your custom data as opposed to writing a well-known file format, you can extend Visit with that. We also have a plugin infrastructure for our operators, which allow you to transform data, in our plots, which allow you to view pictures. There's ways to do custom GUIs. Reskinning Visit is kind of a complicated thing, but some people do that. We have Python interfaces for both driving the tool and for doing sort of low-level computation. And we'll talk a lot about the Python interface for scripting the tool in the hands-on. And then we also have a tool for in-situ coupling called libsim, which works like a magical database reader. And you can link it directly into your code and then memory share directly over memory your mesh data structures. So, Visit, one of the pride points of Visit over the last 10 years, basically the developments that came outside of Livermore, was engaging researchers and getting researchers to productize some of their scalable algorithms into a tool where people can use them. And Visit's been very successful with that through the SciDAC efforts. So the streamline infrastructure in Visit, also called the integral curve infrastructure, is really the prime example of this. Integrating streamlines across a parallel supercomputer, when your data is that's a complicated thing. There's lots of trade-offs, and there was lots of research done in order to get those algorithms right and to support user communities such as the Fusion community. So we have these ongoing efforts. Our current research is more on the boundaries of how we're going to deal with exascale. So looking at how we're going to deal with many core architectures and looking at how we put our in-situ infrastructures on a dyad, because you pull in a tool like Visit. Visit's a giant tool. You pull in a tool like Visit, and now you're fighting with your simulation for memory and resources. So we're focusing on in-situ, and we're working on new solutions for that, and new solutions that will allow us to do lighter weight in-situ with more limited functionality, but lessen the impact on simulation codes. All right, so when you use Visit, and the way I like to describe the interface to people is I like to emphasize there's five things you have to understand. So those 5 things are here. So a database is how you read your data. A plot is how you render your data or how you make pictures of your data. An operator is what you can use to manipulate your data. And then the last 2 are more for quantitative things, and they're also very important. Expressions allow you to generate derived quantities. So what does that mean? Well, if your simulation code didn't write out its mass as a field for you to render, but it did write out its density, with Visit you can compose an expression that multiplies the density times the volume of each cell, and you can get a picture of mass, or you can integrate mass. And queries allow you to summarize data. So they allow you to say, hey, where's the maximum of this value, sum this value, things of that nature. So they give you quantitative information that's sort of not part of this mesh data model. So you can get a 1 number out, but you're not getting a mesh out of a query. To give you an example of how Visit works, so Visit also is pipeline-based, much like ParaView, but we use those 5 concepts. We have the databases, plots, operators, expressions, and queries. These examples give you an idea of how you can compose these concepts a little bit without showing you how to do it in the interface, which is what we're going to do after lunch. But we start with a database. Everything starts with a database, even in situ. In situ is again, a magical database in our model. So in this example, we talk about opening a file. So we're opening some HDF5 file. And then we'd like to make a plot of a field in a field that's on the mesh. So an example of that is a pseudo-color of density. Again, that's what I showed you with that Raleigh-Taylor mixing simulation. That was a density plot showing that the density varies throughout the fluid. But we can also transform our data. So if we extend our example before we were just making a pseudo-color plot of our density, We can instead slice it, so we can have some slicing plane and then just look at a 2D representation of our data or look at a 3D representation of that slice. So to do that, we apply a slice operator. Visit has this big menu of operators for you to choose. You can chain up a whole bunch of different operators. So in this case, we are slicing our data set, which gives us a 2D plane. And then we apply another operator, which elevates it by a field. So you can think of if you've sliced something and you want to make a topographic map out of it, you want to extrude it by the values on that picture. And then again, we render the plot, so we're rendering the output of that mesh. We can also do these derived quantities. So derived quantities are again, expressions. So here's an example. If you want to know the speed of your data set, but that was not saved out, but you happen to have a velocity vector field, you can take the magnitude of that vector field, and then you can get this scalar value, which is the speed, and plot that with a pseudocolor plot. Or you can ask quantitative questions, and the quantitative questions actually happen. They don't really happen after the plot, but they kind of hang off the plot. So if you've plotted the pseudocolor of density, you can, in addition to that, you can integrate the density to find the total mass of the problem. So that's one of the types of query operations you can do. And of course, you can compose all of these things together into very complicated operations. So in this example, we start with our file. We are getting the speed, which is, again, we're doing this derived quantity. We're taking the magnitude of this vector field of velocity. We're slicing it, and then we're elevating it, and we're creating a picture of it. But at the end, we're also asking a question. So what we've effectively done when we slice it is we have a cross-section of the data. So we're going to ask, OK, well, what's the maximum speed over this cross-section? You can ask questions on the data you've transformed. So databases, expressions, operators, plots, and queries, you can compose them all together to ask and answer the questions that you want to from your simulation data. All right, so this is the visit what's the big deal slide. So it really gives you a set of tools that can help you explore your data, help you communicate to other people with what's in your data using plots and things like that, and help you confirm hypotheses. So this is just part of your chain of dealing with your simulation data. And it provides different types of features for different types of people. So again, it's meant to be used by scientists and engineers. It's also meant to be used by visualization people. And it's meant to be used by the people who write simulation codes and need visual debugging tools. That's a good use case. So it's actively developed. We have a lot of people using it. We have a pretty vibrant developer community and user communities. We have these email lists, which are important. So you can find all this information at visitusers.org. And there is a visit users list, which is hosted at Oak Ridge. One of the things you'll find about Visit is, since we are a distributed project, we have various parts of infrastructure sprinkled across the DOE complex, so that's confusing to people, but that's the state of which it evolved. So we have email lists at Oak Ridge, bug tracker at Oak Ridge, certain things at NERSC. So I guess we're geographically diverse with where we're hosting our resources. This is my email. You can get in contact to me with this. I'm going to go ahead and we're going to do the hands-on after lunch, but I just want to tell you again, if you haven't downloaded Visit, you're probably not going to do it during lunch. There'll be some time to do it at the very beginning. But what we're going to do is we're going to be going over these three things. So Visit tutorial basics, the data analysis, and Python scripting. And then we're going to drop into this the water flow tutorial and the aneurysm tutorial and kind of do these narrative-based hands-on exercises. So if you haven't downloaded Visit, maybe fire it off before you go to lunch if you're allowed to leave your laptop here. And the data is there as well. So I'll go ahead and stop, and I'll take some questions, and then we'll get some food. That sounds good. All right, thank you.